Cool, thank you. Yeah, thanks everyone for coming. Before we get started, I'll just say for those of you who are unable to join for part one, or you want a refresher of what was covered in part one, if you go over to our website, PyBaMM.org, and go to the news section, there's a post there about part one of the tech series where you can find the recording and all the notebooks. And there's also a getting started page on our website, which has some video tutorials, and they cover most of the features that were covered in the tech series part one session. So yeah, you can head to our website if you need a refresher or you missed out on anything. We have got the Faraday Tech series Slack channel, which you should all be added to. So you can have discussions in there, and you're welcome, obviously, after this session to carry on talking on Slack to interact with us when you use PyBaMM. Or you can also just type messages in the chat box of the Microsoft Teams, and we'll try and answer your questions there. Okay. So this session is going to be based around two case studies, the first of which is going to be by Ferran Brosser-Plena from Warwick University, and that's going to focus on adding your own parameters into PyBaMM, which I think is something a lot of people are probably interested in doing, is taking PyBaMM and using it for the particular chemistry or cell they're interested in. And the second case study is by Tom Tranter, and he's going to show us an example of investigating cell capacity using PyBaMM. So this is sort of going beyond just taking PyBaMM and running, say, a constant current discharge or running an experiment. He's going to run a whole bunch of simulations and sort of collate the data and do some investigations using that. Just before we get started, we'll just have a quick reminder of the installation instructions. Last week we went through and did a live install for both Linux and Windows. So you can go and look at the video from last week if you want to see that. And all the details are on our website in this getting started page. One thing that I should have updated this slide and I didn't, but last week some people had problems trying to use Python 3.8, which currently isn't supported by PyBaMM, so you can use Python 3.7. But the recommendation is to create a virtual environment, which is step one, just so you don't alter any distribution files on your computer. And then you activate the virtual environment, and then you can just pip install PyBaMM. So that's on a Linux and on a Mac. And if you want to do it on Windows, you can follow pretty similar procedures, just slightly changed the syntax. And you can just install directly in Windows without any extra features or software needed. There are some advanced features, like some of the additional solvers, which don't work in Windows. So for that, we recommend using Windows Subsystem for Linux. But instructions for all of those things are online on our website, so you can go there if you want to take a look. So before I pass over to Ferran, I'll just give you a bit of an overview of both of the case studies that are going to be shown today. And then, yeah, I'll pass to Ferran and then over to Tom for the case studies. And then finally, I'm going to talk a bit about the workflow for contributing to PyBaMM and how to make sure that anything you do contribute to PyBaMM is recognised appropriately. And then hopefully that will leave us a bit of time at the end for a discussion about the future direction of PyBaMM and things that people might think are interesting to include. So in the first case study, we're going to see how to make your own parameter set effectively. So in part one of this session, we saw how to take an existing parameter set and then update some of the values, which is kind of that first image, the block there. And that can get quite messy if you've got a lot of parameters you want to update. So we're going to show you how you can define some new parameter sets that you can just load up for you to use conveniently. So that's the first one. And then in the second one, we're going to vary a key parameter in the model and observe its effect on the performance. So in particular, we're going to look at how varying the thickness of the anode affects the capacity of the battery, and then we can collect the results and play around with that. And I think Tom's got some examples of how to do this in a loop and parallel. So at that point, I'm going to stop sharing my screen and I'll pass over to Ferran for the first case study.
Great, thanks, Rob. So yes, as Rob said, I'll show you how you can change your parameters, but not just from the script, but actually finding your own parameter set, because that's probably something that you might want to do, especially when you run your simulations for whatever chemistry you have, because at the moment we have a few chemistries built in PyBaMM, but of course there's a plethora of them, so might be the ones you're interested in. So I created here, hopefully you can see my screen, otherwise let me know. So I created a Jupyter notebook. I have to say, and I'll remind you closer to the point, if you're using the same repository as last week, you might have to skip one step, but I'll make clear when that comes. So of course, the first thing we do is import PyBaMM. And by the way, I'm following the notebook called 5 new parameter set in the Jupyter have examples for the session. So yeah, the first thing is import PyBaMM, and let's say I want to run a simulation as usual. So I'll say it's lithium-ion, and I'll run in this case SPME, just because it's faster than the FN. And let's say I want to run an experiment, which is just some discharge and some relaxation. So actually, it'll be faster if I just copy, because that's something we covered in last week's session. So far, the same as we did last week. And now I want to set a parameter set that's not the default one. So for example, I'm going to call the parameter set for the LGM50 from Chen 2020. So basically, we define that we want the parameter values from this chemistry, which is one of the parameter sets that come in PyBaMM by default. Sorry, typo here. And then let's say I want to test what happens if I make my battery twice as thick. So all the thicknesses of current collectors, electrodes, separator, and so on, I want to multiply them by 2. So one way to do it, following what we showed last week, would be to just change the parameters one by one. I just copy paste from the example here, but basically you would type and say, okay, the negative current collector thickness, it used to be 12 10 to the minus 6, now it's 24, and so on. And what I did here as well is double the cell capacity and typical current and current function, just because if I make the cell twice as thick, it will double the capacity. So then in order for the 1C discharge to actually be 1C, I need to update what's the cell capacity and typical current and so on. So as you can see here, that's not terribly long. It's 7 or 8 lines of code. But imagine what would happen if you have to define your own new chemistry, right? So that would be about 30 parameters. It'd be really, really long. And it gets pretty bad if you have to do that all the time. Imagine you want to do one simulation, then you want to create another script, and you have to copy paste every single time, or the same 30 or 30 something lines of code. And before showing how to do it, just to say that this way is totally fine, because you can create a simulation and you can solve it. So there's nothing wrong with that. It's just a matter of convenience and keeping your code as simple as possible and as clean as possible, because then it's much easier to debug and to make sure everything runs nicely. So we solve and we plot. So as you can see here, that's totally fine. And just as an example, I did a C/2 discharge, and that's how it's working. But let's say I want to define a new chemistry. So what we can do here, and in this case, I'm only going to change what's the cell geometry, because I'm focusing on these parameters. But basically, if you want to define a new cathode, a new anode, it's the same way, just changing another file. So first, I just define which parameter set I want to start from. So let's say I want to start from Chen 2020. And I define my new chemistry. And if I now look what's in this my chemistry variable, you'll see that it's a dictionary with all the information. So it tells us it's a lithium-ion battery, because remember, PyBaMM can use lead-acid models as well. The cell is the LGM50 Chen 2020. What's the anode, separator, and so on. So this basically points to which files we need to look for the parameters, which files will PyBaMM go and look to pull these parameters. And finally, and that will come in, Robert will talk about it later, this citation field here, which is the one that will give attribution when people want to find out which parameter set they use. I will say, hey, this parameter set comes from this paper. But as I said, Robert will explain that later. So for example, what I could do now is say, okay, I want to change what the cell part of my battery. And let's say I want to use the parameter set called my new cell. Of course, that will not work now if I run the simulation, because I haven't defined what's my new cell. So what we need to do now is define a new parameter set that we'll call my new cell. So actually, when the chemistry goes and pulls the parameters for the cell from this new parameter set, knows what to use. And as I said, you could do that with anything. You could do it with the anode, the separator, the cathode, electrolyte, and so on. So let's go into how we can change these parameters. And here's where I said that if you are using the same directory where you did it last week, you might get an error. So you have to skip this step that I'm going to do now. So what this command does is run the whatever comes in the next lines as if it was in the terminal, right? But we can do it from PyBaMM. So what this will do is this command will pull the whole directory that PyBaMM has about lithium-ion parameters and copy it in our working directory. So if I run this now, and I go and check here, now there is a new file called lithium-ion that contains all the parameters. And the reason why, if you are working on the same directory as last week, and you run that command will break, is because it will tell you, I already copied that. One of the last things we did in last week's workshop was to actually run this command to see where the parameters were. So if you try to do it again, it'll say this directory already exists, and it will break. But it doesn't matter, because the whole point is that we want this directory called lithium-ion to appear here. So now we can manipulate it. Because the way that PyBaMM works is when we tell PyBaMM, go and look for these parameters that you should know where they are, it will first go into the local copy. So for example, first we'll search in here and see if the new parameters we're asking for are here. And then if it cannot find them here, it will go to the ones that has by default, the ones that wherever PyBaMM is installed, it has a copy of all the parameters. And there is a notebook. If you check the notebook we have as an example, it links to a notebook where with more advanced features with that. But basically, to add your new parameter set, you only need this to do that, because now we can just go in here and create our new parameter set. And in the example notebook that we have, you'll notice that everything is in terms of terminal commands, but you can do it here or in your file explorer as well. So let's say I'll do it here. I want to create a new folder in cells and I'll rename it to be called my new cell, because that's how I told PyBaMM that my parameter would be, right? So notice that the structure, it's pretty similar to this. We have a different subdirectory for cell, anode, separator, cathode, and so on. So I'm saying the cell parameters, pull them from my new cell. So basically, inside of cells, I have my new cell. But that's just a folder. We now need to put some parameters in it. So what we can do, it's a CSV file, so you can create your own CSV file, but it's much easier to copy one from an existing parameter set, like this one. We just copy it, and we go to our my new cell and create a new text file. It's going to be a CSV called parameters.csv. That's how PyBaMM knows that here is where the parameters are. And I'm just going to paste it. So right now it's the same as before, but now we can modify that and it will work. So let's say I'll double all these numbers. So that should be 170.4. Sorry, just doubling the numbers so they match the ones I prescribed before. And notice the structure of the folder, which is basically a CSV file, so comma separated, and it says the parameter, what's the value, and then what's the reference, and here it's an optional one. For example, here we have cylindrical, it tells us some extra information. So it's good because the machine can read this file, but we can also, it's easy to read for humans as well. Let me finish changing the parameters. And then down here, I just double the capacity. So now I've modified this file. And again, if you look at the structure here within lithium-ion, I choose which type of parameter I want to change. In this case, for cells, give it a name, define a parameters.csv. And if you wanted to put that into PyBaMM, you would put a README file with the information on which paper that is, so people can easily find the reference. So now what I can do is define my new parameter set. If I go back to my repository, sorry, to my notebook, and I define my new parameter set to be the parameter values that PyBaMM has, but now for my new chemistry, which is, as we defined before, based on the LGM50, but changing the thicknesses of the electrodes and the separators and so on. So now it runs fine. And actually, to check that we actually changed the values, let's say if I look at the separator thickness, it used to be 12 microns, but now if I check, it should be 24 microns. So effectively, it pulled the updated parameters. And now it's everything follows as usual. We create a simulation and we pass through the new parameter values. We define which experiment we want. And again, we can solve and we can plot. And as you can see now, we actually changed the parameters, and it's the same simulation as we got before. That's everything I wanted to tell you today. I'll make a couple of extra points, but before finishing, I want to say in the example notebook, there is a summary, which is basically the bare minimum amount of commands to run the simulation, because of course here it's all spread over different cells, and it might be confusing which ones are actually needed and which ones were just to show capability. So there is like the summary that you can see. The two things I want to say is right now we only changed parameters that are scalars. If you wanted to change a parameter that's a function, then inside of this folder, you would have to define a function with a given name, a Python script that basically is a function. And in the parameter file, let's say here, you would put, instead of that, you would put function and as a string, and then the name of the function afterwards. And let me go back to normal. And the second thing is that if you want to, that's only going to work locally, because this copy of your parameters lives in your computer. So in a way, you don't have to worry, because that's not being added to PyBaMM. It's only in your computer, so you don't have to worry about the parameters being public or anything. If you want your parameter set to be part of the PyBaMM default parameter sets, then you can just either clone. Definitely, you first have to open an issue in GitHub saying you want to add this new parameter set. And then if you are used to coding, you can just clone the repository and copy the parameters in the right folders and then do a pull request. Or if you're not used to that, just let us know in the issue and we'll help you adding the parameters. So that's everything I wanted to cover today for the how to change the parameters. I will give it back to Rob or pass it to Tom, whatever they prefer. So yeah, let us know if you have questions, and I'll be happy to respond them on the Slack channel.
Cool. Thank you, Fran. I'll just wait 30 seconds or so to see if we get any questions coming up from that, and then we'll pass over to Tom. There's a question here from Ivan. Is there any way to look at or change the number of mesh nodes or finite volumes used for the simulation? And the answer is yes. You can do that by changing the number of variable points. I'll see if I can put up an example on my computer to share my screen. But you can pass that to the simulation as an option, basically.
I'll be showing that in my script, actually.
Oh, okay. So Tom will show it later. Yeah, sorry, I didn't have an example loaded at hand, but yeah. So you can change the number of mesh nodes, and at the moment we've got finite volumes in 1D in the through cell direction, and we've got finite elements if you do a pouch cell model. But we're open to other people including different discretizations within the framework. So another question is, if you have some experimental data and you want to convert this to a function for a PyBaMM parameter, what would you suggest is the best way to do this? So there's two ways of doing this. So as Fran sort of showed at the end, for some parameters that are a function, you can use that tag square brackets function and then give the name of a function for the parameter. You can also use the tag data and just pass the parameter directly as data. So you might have, say, open circuit voltage or open circuit potential as a function of lithiation. And then, yeah, so you can either pass that data and then PyBaMM will interpolate that for you. And it's got a couple of different interpolants built in that it can use. Or you can just create your own interpolant sort of offline if you've got a particular functional form you want to choose, or if there's a particular interpolant that you like. So you're kind of free to either fit it yourself, define a function and pass that function, or you can just pass the data directly.
Sorry, Robert, just let me say something else on that. You might just find that even though the two things are possible, in some cases for certain parameters, using the straight it from data might be much slower because it has to interpolate, and if the data is noisy, it might be that the solver takes longer to converge, but it definitely works with both.
Yeah, I think it's probably safest to make the interpolant yourself, because then as well you can then like plot the interpolant and make sure that something crazy isn't happening at the end, and maybe there might be a bit of manual intervention required if you've got some data that's not that great. But yeah, either way is possible, but probably defining the function yourself is safest, I guess, for want of a better word.
Yeah, I actually had a case where I was doing that, and the data was the OCV data, and it wasn't quite defined over the full range of lithiation, and so basically at the limits of that range of data, it was quite sensitive to the noise in the last couple of points.
Yeah,
and just basically having a bit more control over that interpolation is quite useful. I think actually the Chen 2020 has an example of where it's one of the parameters is a data set, isn't it?
Yeah, that's right. Yeah, and you'll see that there's a commented line in there where there's some sort of artificial points added at the end to sort of help control that end behavior like you were talking about.
Mm.
Yeah, exactly. Sorry, just to show that, if you see this is the Chen 2020 for the anode, and as you can see, the OCP for the electrode is passed as data. So that's just this file here, which is a CSV file again, and that's all the data points we measured. And as Robert said, we added one extra point on one side and one extra point on the other, which is basically choosing it to do something sensible based on the data, but because otherwise it extrapolates and it can do something that really doesn't make sense. And you slightly go beyond that, so and the results like make the code break. But actually, yeah, if you are careful with that, it works fine. Actually, all the simulations we did for the LGM50 was interpolating through this data, and as you can see, it didn't take a long time. It's normally more if you have the diffusion coefficient as data, that might be slower because it takes longer for the solver to converge.
I guess it's worth saying on these sorts of data sets, you could be collecting experimental data with a particular cell geometry, and then that would for a given voltage range mean that the different electrodes are in a certain range of lithiation. But then if you change that geometry and maybe make the electrode slightly thinner, then for that same kind of amount of charge, that state of lithiation is going to be a different range. It might push out the bounds. And I think it's something that we've discussed in the development of kind of making the solver possibly throw some warnings when you go to lithiation states outside of your defined range, which we probably need to think about again. Because obviously, with the idea of PyBaMM is it's very flexible and you can change any parameter you want, really. So you could easily sort of accidentally concoct a situation where you've kind of gone out of your experimental range, I guess.
Yeah, I think there's got to be a little bit of user awareness, I suppose, when you go and changing things. But yeah, you're right. We should try and think hard about catching all those edge cases.
Yeah.
But yeah, in answer to the question, you can put data in, or you can fit the function yourself and put that in. Sorry, we got a bit of a digression there, different discussion. So at that point, I guess, should we go over to you, Tom, and then there'll be plenty of time at the end for any further discussion that people want to have.
All right, I'll share my screen.
Thanks.
Okay. You guys seeing my notebook page at the moment?
Yeah.
Okay. So I'll be going through this number 6 notebook here, electrode sizing, which you can find online. And rather than typing it all out like Ferran's done, I know that's quite useful to sort of follow along at the same time, but there's quite a lot of text, so I'm just going to be copying and pasting bits as we go. So I'll start in a blank notebook, but basically I've got the official one open to the side. So this case study, it's quite simple, but it's looking at the effect of changing that anode thickness, as I mentioned just now, on the capacity of the cell. And what we're going to do is just import some packages. First off, PyBaMM, NumPy. NumPy is like the standard numerical Python package, along with SciPy. It's got loads of useful functions in. Matplotlib is a plotting package, and then this IPy widgets. We actually don't need all of these from this, but this is a really nice package for IPython notebooks, which allows you to create plots which are interactive. And we'll see an example of that later, which is really good when you've got, you know, when you're changing parameters and you want to quickly visualize the effect of changing them. So just Shift-Enter to run that cell.
Tom, I think we're seeing your completed notebook. Is that right?
Oh, okay. Right. Sorry. Thank you. There we go.
Thanks.
Okay. So you already got a sneak preview of what the next cell is going to be. Basically, I'm just going to define some lists. And lists are just the most simple thing to contain information in Python. And you can later on turn them into arrays really easily using NumPy and then do more interesting things with them. But these are just basically going to be containers for the outputs of the simulation. And this factor here I'm going to use to just as a scale factor to do some sizing. You don't need to worry about that too much. LP, that's the thickness of the positive electrode, and that's in meters. So that's 100 microns. And then this thicknesses array is going to be basically what I'm going to use as my anode thickness. So we can just kind of see what's in that. And so there's it's going to go from the being equal sized to the cathode to 2.5 times bigger. And then this next one is a long one. So I'll copy and paste and then go through and then we'll run it. So essentially what I'm going to be doing is creating each simulation in each time in the loop. And you might think that sounds a bit inefficient. And there is actually a different way to do this with certain parameters. If you want to vary them, you only need to create the sort of objects of the simulation once, and then you can use an input parameter. However, as we're actually changing the thickness, and that has an impact on the mesh, we actually do need to create that simulation object each time. So what I'm doing is getting this just the height and width, changing that width by that factor that I defined earlier. Working out here the separator thickness, and then what the total thickness of the cell is, my negative, positive, and separator, working out what the volume is, and then what the volume is in centimeters cubed. And then these top cap, top time, that's going to be just a number that increases throughout this loop below as I do a charge and a discharge, followed one after the other for each thickness that I go through. So I've got these two for loops, these nested loops here. And then basically I'm just going to be printing some information each time. This Imag is the magnitude of the applied current, and it's going to be 1 divided by that factor. So we can come and change that and it will kind of be consistent. And then in this line here, so it's basically going to be changing the magnitude of the current there by -1 and 1 to do charge and discharge. And enum is basically an enumeration. So what you do here is you can enumerate over a list, and you get these two things. You get a sort of index of which iteration you're on in the enum, the first variable, and then the actual value of what's in that list as the second value that you can do. So I use that quite a lot. The enumerate statement is quite useful. And then enum I'm going to use to index into the lists later. So within this sort of central for loop, we're doing things explicitly. So I haven't used a simulation object here, but if you go and look at the code for the simulation, it's kind of going through these steps of defining a model, getting the geometry, and then setting up your parameters. And here I've taken the default parameters, which I think is the Marquis 2019 set, but I've overwrote quite a few of them. So I'm updating this dictionary. I'm using these variables that I defined earlier for height and width. And then the thicknesses as well. And instead of using an input parameter, I'm just hard coding it here as that value that I worked out earlier. The voltage cutoffs I've set to be quite a wide range. And then these concentrations, they're more or less what you will find in that data set. But I've just changed them to be kind of nice, easy round numbers just for demonstration purposes. So the maximum concentration in the negative electrode, you can see here that it's quite different. It's basically half that value in the positive electrode. So when the two electrodes are of the same thickness, then the capacity of that positive electrode to hold lithium is going to be basically twice as good as the anode, and we'll see what effect that has when we run the simulation. And then these initial concentrations, this is setting the initial conditions. So effectively, these numbers are half the values above. So it's sort of initialized in a state of half charged. Also, there's a difference in the electrode surface area to volume ratio. Is obviously that's a morphological parameter that's kind of summarized here, which would be characterized by basically the size and shape of the particles in each electrode. And then finally, an applied current, which is what I'm changing in this inner for loop. So after those parameters are updated, we go ahead and process the model and the geometry, and then create some spatial variation, which we got a question about earlier. Sorry, some spatial variables. So this is the number of points in the negative electrode separator, positive electrode, and then also in the particle domain, the number of points in the negative and positive particles. Not sure why those numbers are different there, actually. I'm going to change that to 10 each. So then we go down. We define the mesh with those points that we just defined earlier, discretize it, and set up a solver. I'm using the Casadi solver here, as it's nice and fast, and it should have installed for you by default on Windows when you use the pip install. And I'm using safe mode. So what that means is it's going to basically do a little bit of solving, and then check for any sort of termination conditions. So by default, we have the voltage limits and also the particle concentrations. Rob may be able to tell you a few more off the top of his head, but those are kind of the ones that you would typically encounter at the end of a simulation before you've reached your sort of specified time. So safe mode means that it's going to take smaller steps and then check more often for that. Fast mode is just going to kind of do all of the time points that you set and then not check until the end, really. So I want to be hitting these conditions, and because they're going to be determining the outcome of the simulation and when I vary the thickness. And then I'm appending the solutions into this solutions list, and I'm just using this kind of trick of just putting it in the last position that I've created. So solutions is going to contain one list for each thickness, and then within that a list for each charge and discharge. And then just some printing and some calculations of capacities. So I'm basically just doing Coulomb counting. So I've worked out the time and the applied currents and converting it to milliamp hours. And then specific capacity as well, so dividing by the volume in centimeters cubed. And then finally wrapped all of that in this sort of ticker time function, which is just going to be a very basic way to work out how long all this took. So hopefully now, after all that talking, I can press Shift Enter and it will run and give some output. So you can see this is doing it pretty quickly, going through my different thicknesses, and it's doing the charge followed by the discharge and working out how many hours of simulation that took and what the calculated capacity was via the Coulomb counting. And it's stopped, and now I should have all of my solutions in my lists, and you can see there these nested lists, charge and discharge for each thickness. Now the simulation time was 16 seconds, which, so there was 11 different thicknesses and 2 simulations within each one. So that's not too bad. That's just over like a 1.5 seconds per, just under 1.5 seconds per one. What I'm also going to do is just work out what the maximum capacity was in all the simulations. And I'll use that as a kind of upper limit for the next plotting function. So to then plot all the data together, I've got this plot function. And what I'm doing now is I'm looping through my solutions again. And I'm working out some of that information. But I'm going to be plotting the average extent of lithiation in each particle, which can be accessed from the solution using the variable name like this. So this is now kind of indexing into a dictionary with this key. And also the surface particle concentration, because that's actually more important in a way to the simulation. And we'll see that that's what hits the termination trigger for the first simulation. And then, yeah, just some kind of nice little plotting guff you don't need to worry about too much, but you can have for reference in the notebook online. So that's now defined as the plot function, and to interact with it, I'm going to use the interact widget. And here it's popped up, and it's showing by default the first simulation we did. So the anode thickness here is 100 microns, and you can see that these things that we're plotting on the y-axis is the extent of lithiation, and then capacity on the x-axis. And so charge on the left and discharge on the right. So this negative surface concentration is reaching its like normalized maximum there. So it goes between 0 and 1, and it's quite high compared to the average as well. So there's obviously some basically solid diffusion processes that are going on in there that are quite slow. But we can see that basically the anode has gone from half charged to almost full charged, or the surface is fully charged, but the cathode still has a long way to go. So you can now increment and look through the data interactively and really get like a nice feel for how changing that thickness is going to impact the simulation. And you can see as we make the anode thicker, you're utilizing more of the total amount of lithium in the system, getting up to a higher capacity. And that was quite a simple just demonstration of just changing one parameter and having a pretty big effect on the outcome of the simulation. Just another figure at the end to just show, well, this isn't the whole story, because in terms of optimization, yes, we're increasing our capacity, but our specific capacity has this type of shape. So there's obviously a maximum, depending on what you're trying to optimize for different applications. You might not always want to take that maximum point there. So that was the demonstration of the simulation in the notebook, and then it was just done inside a loop, which is calculating everything, sequentially. It's possible in Python to use parallel processing. Now, Python isn't the best language for parallel processing, and I won't go into the reasons why, but you can do it with a little bit of sort of knowledge about the process. And however, it's even harder to do it in a notebook. So what I'm going to do is actually switch to my Spider interactive development environment. And essentially what I've got here is the same code, but I've put all of the logic basically for running the whole simulation just inside this one function, which I've called battery sim parallel. And all it does is take in the anode thickness as an input parameter, and everything else is hard coded. Now that's quite lazy, but I'm just doing that for demonstration purposes to just show it quickly. So then when you're running, I'm basically making use of the concurrent futures process pool executor package. When you do that, a kind of quirk of Python is that you're writing your scripts and you're pressing kind of go, and then seemingly it just runs. But things in parallel actually need to be sort of what do you call it? Serialized. There needs to be computer code generated and sent off to each processor, so that it can kind of take the whole program and run it, you know, at the same time on different nodes of your computer. So in order to do that, it needs to be defined inside this main, if name equals main kind of statement here, and that just tells it that basically pickle everything. Or pickling is kind of a way of serializing these objects and sending them off. So everything in this script needs to be sent off to each process. And so what I'm doing is I'm setting up this process pool, and then you basically use this map function on the battery sim parallel function that I defined earlier. And then so it takes the function as the first argument, and then the input parameters to that function as a list as the second argument. And the map will just essentially say map to all the nodes available. You can also give it a number of nodes to use. And then around that map function, I've just recorded the time again. So remember that the first time it was about 15 seconds. And now we'll see how quickly it goes. So I'll just restart my kernel. And that was about 3 times quicker. So there's a bit of time actually that needs to be taken up in sort of setting up this parallel process pool. So if you're running, if I was comparing, say doing 100 you know, iterations of the thickness, then the relative speed increase would be even better on this parallel processing. And it's actually something that I've done in my own research. So if we have time, I can show a few slides about that. And I think it is definitely possible to do parallel processing in the Jupyter notebooks. It's just it seems to be a lot easier when you're just running scripts like this. So with the parallel processing, I'll just get actually, I'm sharing the wrong screen now. I'll stop sharing for a second. Screen 2. Okay, can you see that full screen? So essentially, I took an image of a battery, which was collected at UCL with a tomography machine. And so this is like a cross section through a spiral geometry, a cylindrical cell. And what I did was divide it up in this kind of dartboard fashion. So every 10 degrees, there's a node, and then identified the connections around the current collector between these nodes, and also sort of between the layers as well, where the battery simulation is actually defined. And so with this sort of resolution and this number of layers, there was about 1,300 individual single particle models. And I could also use the DFN model as well. And these were coupled together in a kind of like resistor network effect. So it's similar to the 1+1D or the 2+1D simulations that are completely in PyBaMM, except the geometry has been defined sort of externally. and the boundary conditions on each of the simulations is defined externally as well. But essentially, it's a 1D PyBaMM simulation applied many times over this global geometry. And in doing that, I was able to capture some kind of quite interesting effects. It also provides some flexibility in terms of where you apply the global boundary conditions. So I looked at the effective tab placements, and having one inner and one outer versus 5 intermediate stages, and running the model and collecting back the information in parallel and kind of processing it interactively. I could generate these time series plots where I looked at the current collector density locally and also the temperature. And you can see it kind of evolves over time. And based on the proximity of your particular battery sections to a tab, you're going to be essentially pulling slightly different currents out of different sections of the battery at the same time for a given sort of global current, and then that sort of results in these heterogeneities in state of charge, which have an effect on the sort of local resistance, and you get these kind of interesting waves where certain sections of the battery have discharged more than others, and then their local resistance goes up, and then suddenly it becomes less favorable to take charge out of those particular positions. So you get this kind of wave-like nature, and that's mainly dependent on the shape of the OCV curve and also the tab placement defining this kind of circuit resistance as well. So that was just a quick example of 2 tabs, and then you can see the 5 tabs, similar picture, but it's repeated 5 times essentially, and the magnitude of this difference in local current is a lot less because actually the resistance in the current collectors itself is kind of non-negligible. And you can just see that. So yeah, this is a paper that's going to be published soon. I just got the reviews back, so hopefully I'll be able to share that with you. And maybe I've already talked about it actually at the Faraday Club. But it's quite kind of interesting because I was doing this work and I was talking to one of my colleagues at UCL who was doing some work on battery packs, and he was seeing similar kind of wave-like behavior in terms of which cell was discharging more than the others relatively, and this modeling approach is kind of like modeling a pack, really. Like we kind of labeled it as a batteries in batteries approach to modeling a single cell, but the methodology can be applied to packs directly, and obviously the thermal treatments need to be different for a pack, but that's where I want to take this work next. And look at interesting problems for packs too. So that simulation was using it was all written in Python using open source software, and running on a pretty good but not a supercomputer, so just a standard desktop. And those full discharge simulations were computing with the single particle model in about 25 minutes and for 1300, and about 40 minutes for the DFN model, which has more equations to solve. So that's pretty much me, and I hope that was an interesting demonstration of some of the more slightly advanced features that you can make use of with this modeling package.
Cool, thanks, Tom. Yeah, I think that was a nice demonstration. We'll get into that. Yeah, that was nice. I think. Sorry, Tom, you might. Yes. Thanks. Yeah, sorry, I was getting a weird echo there. Yeah, so that was a good demonstration, I think, of how you can use PyBaMM directly to do some different investigations, different studies, and how you can also call PyBaMM up and use it with other software packages. And I think that just highlights one of the things we really wanted to do with PyBaMM was to make it very extensible, either in itself, adding new features and submodels, or being able to use PyBaMM as a package within another simulation. So like in Tom's JRO model, PyBaMM was called up as a tool to do the local electrochemical modeling. So hopefully there's a lot of different use cases that you could imagine PyBaMM would be useful for. So just before we finish, I'm going to share some slides on the workflow for contributing to PyBaMM, which should probably take a couple of minutes. So then we've got a good chunk of time at the end for any discussion that people want to have, and that can be pretty open. We'll sort of take lead from you guys about what people want to talk about. And if people don't want to discuss things, then obviously you're welcome to leave. So I'll just share my screen again now. Okay. Right. So contributing, can people see the workflow here? I'll go with yes.
Yeah.
Cool, thanks. So typically the workflow would be something like you create an issue on the GitHub repository where you propose the new feature that you want. But I've just got a little speech box there. We've had some questions about people who want to work on things in private or are concerned about, not wanting to put their ideas out there on the internet, and particularly, if you've got some novel idea, you might not want to post an issue on GitHub saying I've got this great idea and I'd like to do it. So obviously, if you'd like to do something in private, you can just get in touch with us via email or Slack or whatever, and we can figure out how to do that. But if you are happy to do something public, maybe you've already got the publication out and you just want to add it into PyBaMM, or it's just some feature that you're happy to share, then the workflow is to create an issue on GitHub where we can discuss this proposal, or maybe give you some guidance about the best way of doing something. Then you can create a branch of PyBaMM on your own fork where you can work on the changes that you want to make. Then you can implement your work on this fork. This is all just on your own sort of computer or on your own copy of PyBaMM. You can implement all your equations and blah, blah, blah. Something that's important if you want to make sure you're getting credited for the work that you're putting into PyBaMM is to add a reference to the file citations.txt. So this is this fourth image on the workflow on the right here. You've got this BibTeX entry, so it's an article with some key and title and the authors and so on. So you can add any relevant references for your work into this file. And then the really key part is to make sure that you register these citations in your code when that particular publication is being used. So you can use this command PyBaMM citations register, and then the key for the article, for the BibTeX entry. And what that means is that when someone uses that piece of code, basically PyBaMM will tell them afterwards, oh, in the piece of code that you used, you need to cite this publication. So just make sure that you're getting the appropriate citations for your work when people are using your code. Another very important step is to test all your code. So we've got a big testing suite. You can look at other tests for examples of the kind of tests you might want to do, just to make sure your code works and sort of protect your code against changes in the future. So, you might put some piece of code in, it works great, and then someone in the future might change something somewhere else that breaks your piece of code. So you just want to sort of protect yourself against that. So testing it is very important. And then once you're kind of happy with your work, maybe you think it's totally done, or maybe you think it's mostly done, but you'd like some sort of pointers, you can create a pull request to merge that into the main code repository. And then someone from the PyBaMM team will review that code, and they need to accept it or approve it before it can be merged in. So there's a good sort of procedure in place to make sure that people aren't just adding nonsense into the repository. So that's kind of the general workflow. And at any point along this workflow, obviously you're welcome to get in touch with us via email, Slack, have conversations on GitHub about what to do. We were pre-lockdown holding implementation days where if you wanted to work on something, you could arrange to come to Oxford, or we could come somewhere else with someone who's more familiar with PyBaMM, and they can sort of sit down and help you do what you want to do in sort of like an intense session, I guess. I think we're still offering those virtually if people would like them. So if you've got something you really want to put in and you've got an idea, but you just need a bit of help getting it done, then again, get in touch and we can arrange time to help you out over the internet. So here's just an example about ensuring your contribution is credited. So it's an example of Ferran. So he added this LGM50 parameter set that we saw earlier in his case study, and he added his reference to the paper, this Chen 2020, in the citations file. So then if you run this code snippet at the top here, you use the parameter values from Chen 2020, and then you type out this command PyBaMM.print citations at the end of your script. What that does is it returns all of the BibTeX entries for the papers that you used. So in particular, it will return this Chen 2021, along with a whole bunch of other references to do with SPME and the solvers that you've used and everything else. But this just makes sure that someone is referencing all of the correct papers. So hopefully that gives people a bit of reassurance that their work isn't going to go unnoticed, and their contributions to PyBaMM won't be credited properly. And sort of on that point, whenever you do anything on this workflow, you're totally in control of when you choose to put this into the main branch. So if you want to work on something and never put it in, okay, that's fine. If you want to work on something and wait until your publication is accepted and then put it in, that's also fine. And that's kind of the recommended workflow, is to work on your problem. Maybe you use PyBaMM to do the work for your publication, but you wait until your publication is out before you merge it into the main code repository so that people can cite your paper. But again, if people have got questions about contributing, then just get in touch. So finally, I've just got a slide on a few of the things we're currently working on, hopefully to prompt a bit of discussion. So things we're thinking about are EIS and sort of automating that. Degradation mechanisms. So we've got some SEI models. People are thinking about lithium plating. People think about including mechanics into the problem, and that's coupled to either temperature, so sort of thermal expansion, or lithiation. We have been thinking about other geometries as well, and like Tom talked about, he's thinking about packs. So this is either other geometries directly in PyBaMM or exploiting PyBaMM as a package in other simulations to do more complicated geometries. People are thinking about other chemistries and also thinking about things like fuel cells. We've got a point there on spatially structured electrodes. So currently you can do things like porosity and particle size as a function of position in the electrode, but there's other things people are interested in making functions of space. So it's trying to include a bit more of that morphology of the electrode, I guess. Parameter estimation obviously is a thing lots of people are interested in, so we're trying to make it as easy as possible to use PyBaMM for doing that. And link things in with experimental data, make it easy for you to use PyBaMM to replicate your experiments and compare to your results. And we're always looking for improvements to the framework. So if you use PyBaMM and you think the way you've done this is really stupid, or it'd be much easier if I could do something differently, then again, make an issue and make a suggestion, and we're happy to take that on board. So before we have the discussion, I'll just advertise the next Faraday Tech session, which is on the 11th of June, which is 2 days time, IP from a commercial perspective. There may be some more sessions after that. I've just not updated my slides since that was the only one in the future when I last made them. But I'll say thank you all very much for coming, but now we've got a good half hour left for discussion. So if you've got questions, if you've got things you want to discuss, then obviously stick around and we can have that discussion. But if not, thank you very much for coming, and please keep in touch on Slack as you carry on using PyBaMM. Oh, and thank you to Fran and Tom as well for presenting the case studies.
Thanks to all three of you. That was really good.
Cool. So we've got some questions coming in, so maybe I'll read the questions out for people, and then people can jump in and answering if they've got things to add. So one question is, how can you test which parameters your performance, i.e. capacity, is most sensitive to? So I guess you just have to run the simulations. So Tom showed this simulation where you just created lots of simulations, hard-coded it with a different parameter. But there's also these things called input parameters. So you can, like when we changed a parameter value to a different number, say Fran doubled something from 12 to 24, you can actually, instead of putting a number in, you can tag it as an input, and that tells PyBaMM that you don't want to set the value for this until the time of running the simulation. And this kind of lets you either quickly just run lots of simulations by changing that parameter without creating the simulation every time, or it lets you wrap the PyBaMM simulation in some optimization routine, so you can do some optimization directly over that if you've got some function you need to minimize. We are working on getting out some useful stuff for parameter estimation. So for example, the way the models are all stored in PyBaMM are as expression trees. And what that lets you do is calculate the Jacobian of that tree, and you can differentiate that tree with respect to parameters. So you can get the sensitivities out of a model as well. That's not totally finished yet, but that's sort of coming up in the future to be able to do sensitivity analysis directly in PyBaMM. But hopefully that sort of goes some way to answer your question. I've got a example notebook that shows how to wrap an optimizer around PyBaMM, a derivative-free optimizer, which I can share with you if that's of interest.
Yeah, that's definitely of interest. Sorry, I realized I picked a bad parameter to show actually, because it meant that I couldn't use those inputs because I was actually having to change the mesh, as I mentioned earlier. But most of the parameters in PyBaMM you can wrap as inputs and then vary without having to recreate the simulations, as Rob said, which is a really useful function.
Yeah. Yeah, I can't find that notebook I was talking about right now, but I can send that over an email or something, or put it in the chat to show you how to do that. Okay, so next question. There's two questions here. One is how to change the electrode material and separating material. What if the materials are homemade materials? So in answer to that question, so Ferran showed how you changed the cell for a particular chemistry, and he said, "Oh, cell, I'm going to call it my new cell, the string." But when he opened up that dictionary, it had different components. It had like anode, cathode, separator, electrolyte, and you can swap and change all of those components. I would say freely. I guess there's some combinations that, you know, if you pick randomly one anode from one publication and a cathode from another publication, maybe the simulation might do something funky because those things aren't really compatible. But in principle, you can pick any different cell components you want just by choosing the correct name. So if you copy that lithium ion folder of parameters in, and it's got, you know, the folder of anodes, you can pick any anode from there you like and swap and change those out. And if it's a homemade material, in the same way that Ferran showed, you could copy the CSV file for the cell to put in some new cell geometry. You could copy and paste the CSV file for an anode and put in your own parameter values in there. Or if you've got something, you know, you don't necessarily have to go down the route of defining it by those separate components. You can, if you want to, just define all of your parameters in one file. If you look at the documentation for the parameter values class, it shows you how to just put in some values. So if you've just got 30 parameters in your model and you just want to tell PyBaMM these are those 30 parameters and these are their values, you can do that as well. I'll answer the second question and then I'll see if anyone else has got input on either of those. The second question is it possible to do half cell analysis or pouch cells? We've not got half cells in at the moment. There is an issue open for that because someone else is interested in it. So if people are interested in adding that in as a feature to PyBaMM, then that would be great. And I think it would be relatively straightforward. I'll say relatively because I haven't tried, but in principle, it should be straightforward to be able to extend it to half cell models. Pouch cells, yes, you can do pouch cells. In the sense we call them 1+1D and 2+1D pouch cells because it's kind of a model where the through cell behavior and the transverse behavior in sort of the plane of the current collector are kind of decoupled. So it's kind of like solving a 1D DFN or SPM model, whichever you choose, at each point on the current collector, and then they're all coupled together via the current collectors. But I've got a preprint on that I can send over to you if that's of interest. Yeah, has anyone else got any input on either of those questions?
About the half cell, I would say, as you said, at the moment it's not implemented. Though, if it's like it shouldn't be hard to hack it to get it working if it's something urgent. But definitely, it's something I think it needs to be implemented and it shouldn't take long. So there are two routes: either define a anode that it's basically a lithium foil, and you could probably set the parameters accordingly to that, or just a proper model, which hopefully it will come soon.
Cool, thanks.
I was going to add on the pouch cells. Is it the current framework is basically a single layer pouch cell? Is that correct?
Yeah, that's a good point actually. Yeah, so it's a single layer pouch cell at the moment. Yeah.
But an approach similar to the one I showed for the jelly roll could be used to do multiple layers and different geometries.
Yeah. So next question is, I opened discretization file and read m and then t dot equals f of yt, and then Jacobian is df dy. So I began to wonder, is it approximating an equation by a linear one and not Runge-Kutta here? So it depends what solver you're using, what it does, but I mean, all of them are doing some kind of Newton iteration or similar. and that's where the Jacobian gets used. So, all of the governing equations are non-linear, but at some point you need to do some linear solve, by Newton or whatever you like. Different solvers have got different options, and you can kind of play around with the back end of those a bit. But you get that Jacobian is sort of the analytic Jacobian in that, it's not an approximation to the Jacobian, it's actually computes that directly from the model equations automatically for you. But that's where that's used. Hopefully that answers that question. Okay, so next one is how to set the initial condition for a charging from empty experiment type. So the initial conditions are provided for the concentrations in the particles. So I guess you just have to look at the parameter set and see what the minimum and maximum concentrations are for the two electrodes, and accordingly change the initial concentrations to correspond to a charge from empty. I think there is some discussion about making some kind of helper function for setting initial conditions in a more easy way. Maybe I've made that up, but at the moment you just have to change the initial concentrations in either electrode to correspond to empty start. I don't know if anyone has anything to add on that.
Actually, you could. I think there is an issue on that, as you said, Robert. But if you want to define the initial concentration from empty as the initial condition from empty as some voltage, you could do some preliminary simulation, which you take whatever is your initial condition, you discharge your battery, and you hold it at that minimum voltage, that let's say 2.5 volts, if that's your empty, just to make sure, and you hold it there for like a long time, and that will bring your battery to fully empty, and then you can either continue the simulation from there or just probe your simulation to see what was the final concentration, the concentration at this empty state, and use that to plug in. Because it's, as Robert said, it's hard to translate from voltage to concentrations, and currently the only way to pass in initial conditions is as concentrations.
Just on that as well, it is possible to save a solution and then reinitialize a new simulation based on that old sort of state as well. So that might help.
Cool, thank you. And another question is, what finite element meshing do you use or plan to use? So at the moment, the only finite elements we've got are in the current collector dimensions in the pouch cell models, and that is just piecewise linear elements on a sort of triangular mesh from using another package, Scikit FEM, I think is the name. I might have got that wrong. So that's just using another finite element package. I don't know if anyone of the sort of core team is particularly focused on adding new spatial methods at the moment. That is something we'd be very much open to having contributions from other people on. So if people are really interested in adding new spatial methods, that'd be great. So another question is how to set the discharge rate to 1C. So at the moment, if you just run a simulation with defaults, then it discharges at a rate given by the cell capacity, which I guess should be approximately 1C. So you just look at the cell capacity and then have like a nominal 1C rate based on the cell capacity. If that gives you what you want. But yeah, you can change the input current. I guess maybe there's a bit of playing around you could do to make sure that actually matches up to discharging an hour, because if you discharge at the rate given by the cell capacity, that might not be exactly an hour. So I suppose it depends how precise you want to be. Maybe, I don't know, maybe someone's got something more insightful to add to that.
Yeah, I guess we've defined these the cell capacity in terms of going between two voltage limits, so having an upper voltage limit and a lower voltage limit, and however much capacity you can remove as in 1 hour for a 1C rate, roughly. We define that as a capacity. So it's, yeah, I think that's how we kind of define the 1C rate for ourselves.
Yeah, so you need to adjust the current manually. You can pass a C rate to the simulation class, but all that will do is look at what the cell capacity is and then multiply that by the appropriate number. But that's, yeah, as Scott said, that's defined for a particular voltage range. So if you start changing other parameters, you might just need to manually adjust the current to sort of tweak that to the right thing if you change parameters.
I know everyone really likes C rates, but they're quite annoying from a modeling perspective because the capacity does just vary based on your operating conditions and your limits that you want to operate within. And yeah, it's a bit safer to define the current, I guess, and stick to that.
And yeah, the parameter you want for that is called current function in amps. So that's the one that will change the actual current that's applied. And then, yeah, as you saw last week, if you were here, or if you go back and look at the recording from last week, that current function can be a scalar if you just want a constant current, charge or discharge, or it can be some function of time if you want to specify some time varying current, or it can be some data if you've got a drive cycle you want to run. But there's a notebook on that, and yeah, it was covered last week if you're interested. Cool. So it looks like that was probably our last question. But yeah, feel free to ask more questions on Slack or on GitHub if they come to mind later, or if you start experimenting with PyBaMM and yeah, you just think of a question later. There's normally someone online to answer your queries. But yeah, if there's no more questions, I guess we'll finish there. And thank you very much for coming. Oh, another question. Okay, cool. What interpolation methods, non-PyBaMM, would you recommend for defining your own functions? Good question. I don't know. I mean, default is probably like some kind of spline, I guess, but it depends whether you want to like overshoot your data. So some interpolants make sure that you're sort of capped at what the maximum and minimum are in your data range, so you won't kind of overshoot like you would if you fitted like a cubic polynomial or something. And there's like a p-chip interpolator that does that. But I'm not super. I haven't really done a lot of that myself. Maybe someone else has got something. Fran, maybe have you got any recommendations, or someone else who's more experienced in doing that, I guess?
So the experience I have on that, I think that the one that comes by default in PyBaMM, but I'm not totally sure, I would have to check, is the p-chip one that comes from in SciPy as the default one. So of course you could use any of the SciPy ones and should work pretty straightforward. But the question on which one is more suitable for your data, I guess that's more something that you will need to try and see how it works. For example, as I said, for the OCV, I found that it might throw some issues if it was extrapolating. There are some issues with the algorithm that might throw an error if it's solving and it extrapolates, but also some issues of it just extrapolating. And as Robert said, because it's a cubic, it does something that makes no sense. For example, you could have that suddenly the OCV, as you go, for example, for the cathode, as you go to lower states of charge, which should go about 4 volts for example, NMC 811, and then suddenly drops to -3 volts, which of course doesn't make any sense. So you have to be careful on that. And I don't have a magic answer. So I would say test it with your data, and it can be helpful as to plot with your solution actually what's the OCV doing as you run the simulations, because that will help spot any weird behavior.
Okay. Another question is, are the parameters that we can alter independent of each other? How to find out if any of them are coupled and have to be changed simultaneously? So you can change all the ones that are in the CSV files independent from each other, but there are certain things that maybe you don't want to. So in particular, things like the surface area to volume ratio, might assume spherical particles, but it's in there that you can change it independently, because you might change that value as a bit of a fudge for accounting for non-spherical particles or something. So in principle, you can change them independently, but I guess just be a bit aware of where the physics come from and make sure that changing them independently makes sense, or be aware of what that means. So there are some assumptions about how certain parameters might relate if you've made, yeah, I think the best example is the spherical particles one. So at the moment we assume spherical particles, but you can independently change radius, surface area to volume ratio, porosity. And the reason you might do that is because you might tweak one of those things to fit some data that had to account for non-spherical particles or something. So they're in there to allow sort of parameter fitting, but be aware where they come from, I guess, is an answer.
Yeah, another one that might be tricky is if you change anything related to the maximum capacity or the thickness of the electrodes and you don't change the cell capacity, because of course that will go up with that. So that would mess up your C rates in a way. So if you remember in my example, I changed the thicknesses and then I changed the capacity to match accordingly. So yeah, you have to be aware of what actually means in terms of the model, because many things are related.
I think maybe we should consider renaming that to nominal capacity, because that's what a lot of battery manufacturers state it as well. And it really doesn't factor into the simulations that much, does it? That parameter, apart from if you specify a C rate instead of an amp. But I was going to say another couple of parameters that should probably always get changed together is the OCV and the entropic coefficient, the du dt.
Yeah.
Because you change one of those randomly, the other one is not going to be relevant, basically.
So I've got a follow-up question here is, do you need to define a nominal capacity? So I think what Tom was saying is that basically the thing that we've called capacity is basically a nominal capacity for that cell.
So can you correct me? Is the only thing it's used for in changing one boundary condition to from a capacity to a C rate to an ampage? Is that
I think so. Yeah.
It's used for. Yeah.
Yeah.
So
it's just there to give you what a sort of 1C rate is nominally.
So the answer to that is kind of, I guess you need to give a nominal, you need to give a capacity, but you don't actually need to use it properly we don't actually need it for the simulation if you just supply a current instead of a C rate.
Yeah. Yeah, I think you're right, Tom. Maybe we should call that nominal capacity just to avoid confusion. Yeah. So, okay, so it looks like I've got no more questions. I guess one thing I'll just point people to, I'll just share my screen again before you go. Come out of that. So if you go to our website, PyBaMM.org, and then at the top there's a link. So here's the getting started guide that I mentioned earlier. So we've got installation instructions, and if you click various links for different operating systems. And there's a whole bunch of video tutorials that cover a lot of the things we did in part 1 of this tech series session. There's also a cheat sheet, which we're kind of adding to with some useful things you can do. But in particular, if you click examples at the top, this will redirect you to our examples repository, where there's loads of notebooks and scripts that you can take a look at as examples of things to do. So got notebooks about creating models, about spatial methods, model options, blah, blah. So there's a whole bunch of things in here. So there's lots of places you can look for different things to do. So yeah, it's probably a good place to start if you're thinking about using PyBaMM, but you're not sure what it can do or what you want to do with it, is to go there, look at examples and sort of play around with them. Another question coming in is, will the recording of this seminar be shared? Yes. We'll post it in the Slack, I guess, and maybe it gets emailed around as well, I'm not sure. But it will be shared somehow.
Yeah, I usually send an email with the link to the video. Yeah.
Perfect, thank you.
Okay, great. I guess we can finish there if there are no more questions. Thanks everyone for coming, and feel free to continue asking questions later on in the Slack channel. Thank you very much, Tom, Rob, and Farhan. That was really good. And have a good day.
Thanks, CT.